Welcome back to this module on dynamic exploitation of ILP. The purpose of this lesson is to give you an introduction to dynamic branch prediction. This and the next two lessons are based on section C.2 in Appendix C of the textbook by Hennessy and Patterson. They are also based on the technical report Combining Branch Predictors by Scott McFarling. This report can be found on the internet and I strongly recommend you to read it. Before we delve into the details, a bit of motivation. Tomasulo's algorithm stops issuing instructions after branch to make sure that control dependencies are enforced. As a result, branches reduce performance. Loop unrolling, as we have seen several lessons ago, reduces the number of branches and hence the number of branches it stalls. However, loop unrolling is a compile time technique that cannot be applied to existing legacy codes where only the binaries are available. In this lesson, we therefore consider dynamic, meaning at runtime, branch prediction. The idea behind branch prediction is to predict the branch direction, taken or not taken, before the branch is actually executed. This idea is based on the history of a branch. For example, if the branch was mainly taken the previous times it was executed, we predict it will be taken again. The processor then starts fetching and issuing instructions from the predicted branch direction. As an example, this figure shows the pipeline organization of the IBM Power 4 processor. I will not describe the details of all pipeline stages, but I would like you to observe that branches complete 12 cycles after they have been fetched. As a result, the delay between fetching a branch and executing it is 12 cycles. To reduce the branch penalty, the Power 4 processor performs branch prediction, as all modern high-performance processors do. The branch prediction, the BP stage, performs branch prediction. If the prediction was correct, then there will be no or only a small branch penalty. If the prediction was incorrect, however, there will be a severe branch penalty. As said before, the idea behind branch prediction is to predict the direction, taken or not taken, of each branch. This prediction is based on the history of the predicted branch and maybe other branches as well. The processor then starts fetching and issuing instructions from the predicted direction. If the prediction is correct, there will be no or just a small branch penalty. If the prediction is incorrect, however, the wrongly fetched and issued instructions need to be flushed and the processor needs to start fetching and issuing instructions from the other branch path. In case of a misprediction, there will be a severe branch penalty. The simplest dynamic branch predictor is a 1-bit branch prediction buffer or branch history table. A branch prediction buffer is a table of 1-bit entries. This table is indexed by the lower bits of the program counter. In other words, it is indexed by the lower portion of the branch address. If the index entry is a 1, the branch was taken the last time it was executed, so the entries are set when the branch is executed. If the index entry is 0, on the other hand, the branch was not taken the previous time it was executed. The table is very much like a cache, but it has no tags. So a certain entry can contain the prediction for another branch than the branch we want to predict. Although this reduces performance, for correctness it does not matter, since when the branch is executed, it is checked if the prediction was correct. Furthermore, this scheme only reduces the branch penalty when the branch target address is known before the branch direction. In the canonical 5-stage pipeline, both the branch target address and the branch direction are computed in the decode stage, so this scheme does not improve the performance of the canonical pipeline. Finally, I remark that the prediction is just a hint. If the prediction is correct, there is no branch penalty. If it is incorrect, there can be a severe penalty. To give an example, here is the branch history table. It has 8 entries, so we need 3 bits to index it. And here's the program counter, the address of the branch instruction. Since all MIPS instructions are 4 bytes long, the last 2 bits are ignored, and we use bits 2 to 4 to index the branch history table. The decimal value of these 3 bits in this example equals 6, so we index entry 6 of the table. The bit stored there is a 1, so the branch is predicted taken and the processor starts fetching and issuing instructions at the branch target address. One-bit branch prediction schemes have a problem, however. They cannot deal with nested loop. To illustrate this problem, consider this code snippet, which is a code snippet from the motion estimation stage of an MPEG encoder. It computes the sum of absolute differences of two image blocks. Focus now on the inner loop, highlighted in red. The behavior of the branch implementing this loop is as follows. It loops 16 times and then it exits. Then it loops again 16 times and then it exits again. And this is repeated several times. The shortcoming of a one-bit branch predictor is that it mispredicts twice per iteration of the outer loop. It predicts incorrectly at the end of the inner loop when it predicts looping but the loop exits, and it mispredicts the next time the branch is executed when it predicts exit, since the prediction bit has flipped but the loop loops. So the one-bit branch predictor achieves an accuracy of 14 out of 16 predictions, or 88%, but the loop loops 15 out of 16, or 94% of the time. To remedy this weakness, 2-bit prediction schemes are often used. In a 2-bit scheme, the prediction is changed only if it mispredicts twice. A 2-bit scheme is also called a bimodal predictor. This figure shows the organization of a 2-bit branch history table. Now each entry consists of 2 bits. The example 1-bit branch history table had 8 entries, so a 2-bit table with 4 entries has the same implementation cost. The behavior of each 2-bit entry can be represented by a finite state machine as shown here. The 2 bits are used to encode 4 states. The leftmost bit indicates the prediction. When it is 0, the prediction is not taken. When it is 1, the prediction is taken. It can be seen that in this finite state machine, a prediction must miss twice before it is changed. Suppose, for example, that at a certain time the state is 1, 1 as indicated by the red arrow. So the prediction will be taken. If the prediction is incorrect, the state will change to 1, 0, but it is still predicted taken. Only if it mispredicts again, the state will change to 0, 0, and therefore the next prediction will be not taken. In some textbooks and scientific papers, you may come across this finite state machine, which has a slightly different structure. In this implementation, the finite state machine is implemented using a 2-bit saturating counter. If the branch is taken, the corresponding table entry is incremented but not past 3, and if the branch is not taken, the corresponding entry is decremented but not below 0. Experimental results, for example in a paper from 1986 by Lee and Smith, show that the two FSM perform almost the same. This scheme can also be generalized to an n-bit saturating counter. If the counter is less than half its maximum value, the prediction will be not taken, and when it is greater than that, the branch is predicted taken. But again, experimental studies have shown that 2-bit schemes perform as well or almost as well. For that reason, most processors use a 2-bit scheme. This completes this lesson. Thank you for watching. In the next lesson I will discuss more advanced branch predictors. Hope to see you back.